Hello, good day, everybody. You're welcome back to my channel. I'm sure you've been having a swell over all my videos. It's been impactful and meaningful. Am I certain of that? I'm sure certain of that. Okay, good. Thank you for your feedbacks. Quickly today we'll continue with elasticity. Another elasticity we'll be considering the concept work done in springs and elastic strings. It can be spring, it can be strings, but they are elastic ones. So, what is work done in them? Before that, in the previous video where we worked on elasticity, I've been able to make it known the definition or the meaning, the concept of elasticity. Beyond that, able to relate the formula, that is the force applied to the elastic material is directly proportional to the extension experienced by that body. And that now implies that your F can be equal to a constant being introduced times the extension. Well, here now, we are going to be talking about the work that is done in an elastic material. Now, when work is done, there are two formulas we can use. Majorly, we can consider the work done to be equal to, I've written it here, half of Fe. That is half of the force, half of the product of the force and the extension. Or if you are given a constant, you just use what? Half. Yes. If you, from your formula of F is equal to Ke, if you are given, you make K subject of formula, you're going to be having Ke squared. I'm sure we are good to go. Let's move on to the question we have on board. Look at this. Example 1. On top of a spring of force constant 500 Newton per meter is placed a mass of 5 times 10 raised to the power minus 3 kilograms. If the spring is compressed downwards by a length of 0.02 meters and then released, calculate the height to which the mass is projected. Look at this question very well. We are not doing anything there than to relate it to the work done on the spring to the potential energy possessed by the spring. And here, the work done on the spring, the work done is equal to the potential energy in the spring. If I don't need to write that, because we know, of course, we're dealing with spring. Am I good to go? So, what do we do now? The next thing we'll do, like I've always said, I've always been an advocate of detailed explanation and detailed solution. And how do you have a detailed solution? You write out the parameters. So the first one, on the top of a spring of force constant, our K force constant is 500. It's placed on a mass of 5 times 10 raised to the power minus 3 kilograms, compressed by an extension of length. That is an extension. The extension is 0.02. And then release. Calculate the height. Yes. Calculate the height to which the mass is projected. That's the new length. That's what they are looking for. Not just the new length. The total length that is now having. That should be your L1 plus L2. And that will be your L2 rather. That will be your L2. But we are not dealing with that now because we are dealing with work done in that spring. So H is what we are looking for. But if you have this formula, the work done by a body by virtue of extension or motion is half ke squared. Your kinetic energy, then the work done by a body by virtue of rest, or by that body done in the body just by it lying down, is mgh. Can you see that? So how do we move? It's simple. We put out those formulas, let me rewrite them, then we'll solve. So that is how we'll solve our question. So let me write it here. Half ke squared is equal to mgh. So I have half times 500 times 0.02 squared. That can be equal to what? 5 times 10 raised to the power minus 3 times 10. G is acceleration due to gravity. Then times h. So what do we have? This becomes 250. If I don't, let me just punch my calculator. Punch yours too. You punch your calculator, you're going to be having what? You're going to be having 250 times 0.02. What do you have? 250 times, okay, first you can just change this. There's 0.02 times 0.02. What would that give you? 0.004. Then times 250. That will give you 0.1. So we have the 0.1 being equal to this 1 times 10 will give you 5 times 10 raised to the power minus 2 to reduce the power by 1. So then times h. So your h can be equal to 0.1 divided by 0.05. And that should be equal to what? That give you 2. It should be in meters. So the height attained by that spring is 2 meters. Is that gotten? I'm sure it's gotten. Thank you. So we go to the next example, and there what do we do? We have the question stating that. The question says, a load of 20 newtons of 20 newtons on a wire of cross-sectional 8 times 10 raised to the power minus 7. Yeah, there's an error here. This is just times 10. Don't mind me while I was typing. So you just have 8 times 10 raised to the power minus 7 meters squared. That is the area. Produces an extension of 10 raised to the power minus 4 meters. Calculate the Young modulus on the material of wire if its length is 3 meters. Of course, you should know Young modulus is equal to what? Stress. Let me just write stress. Tensile stress upon tensile strain. You should know that. And stress itself, stress stress is equal to what? Stress is equal to the force applied on that body with respect to the area, and strain is the extension. Yes, the extension with respect to the length. So this is what we are doing. Force over area divided by extension over length. This is what we're going to be making. That's what Young modulus says. That's Young modulus. So we go with this now. We write out. Look at the question. We have a force. We have our area. We have an extension. We are calculating. Okay, yes. Young modulus for the material of the edge. If its length is, the length is 3 meters. So all you are just put these parameters together, then we are good to go. So let's go. What do we have now? We have let me just rewrite that. That's Young modulus F over A divided by extension over length. So that means what? By the time this one changes multiplication, you have length over extension. So we have times, we have length over extension. Our force here is 20. Our area is 8 times 10 is to the power minus 7 times 3 upon what? The extension is 10 raised to the power minus 4. Isn't it? So that will give us what? 60 upon this, by law of indices, 10 raised to the power minus 7, 10 raised to the power minus 4. That gives you 8 times 10 is to the power of minus 11. Yes, that's what that will give you. So if you have that, what do you have? All you have to do is to punch your calculator. Punch your calculator. And that can also be done to be, this is also equal to, let me clear this base, okay. This is 6 times 10. This is times 10 raised to the power 1. This, bring this up, you're going to be having what? 6 times 10 raised to the power 1. Then minus, open bracket, minus 11. You see that? Then everything over 8. You see that at all? So that's what do we do there now? Permit me, I have to clear this place. So if you have that, what is our final answer now? So you have 6 times 10 raised to power of that. So what do you do? So here, sorry, let me wipe this. 1 minus minus 1, that becomes 6 times 10 raised to power 12. Can you see that? Now divided by 8. Just divide 6. 6 divided by 8 is what? The 6 divided by 8. That will give you 0.75. So that becomes what? 0.75 times 10 raised to power 12. What do we have there? That will amount to what? Then you move on, write on, write on, write on. What do you have? You can re-express this as 75 times 10 raised to power minus 2. This order, and then times 10 raised to power what? 12. So what do you have? You're going to be having 75 times 10 raised to power 10. Are you getting that? Yes. That's what you're going to be having. Or you just say 7.5. What we're going to look at 7.5 times 10 raised to power 11. So you think Newton per meter. That's the unit for young modules. So it's as simple as that. We are done without calculator. Yes. So thank you for joining me. Please keep subscribing to my channel. I remain your humble self, my humble self, Edu Ada. If you want to reach me on my contact, the same number, you can reach me via WhatsApp, Telegram, and you can give me a call on it. The Nigerian contact. So you have 081 64 86 9470. Thank you for staying with me. See you later.